Hi, I'm Nilas Dinis, and I'm here to talk about hassle-free nanoparticle characterization with Stenner. Meet Stenner, our unique platform that has applications for quantification and sizing on adeno-associated virus, protein, nucleic acids, and nanoparticles. In this presentation, we'll focus on nanoparticles. One of the first things people notice about nanoparticle samples is that they're really turbid, often so cloudy you can't actually see through them. Just like fog rolling in on the Golden Gate Bridge, you know that if only cloudiness were less of a problem, you could see some really spectacular things. Today we'll look at how you can cut through that cloudiness in your nanoparticle samples to gather some really spectacular data. There are a lot of properties that are important during development of nanoparticles. What particle shape you want and what size they should have, which lipids or other components will be used and in which ratios. Choosing your API payload, choosing potential surfactants, what charge the particle should have, in which buffer, and which pH it should be in. Now, once the particle is made, two important questions come up as well. What is my particle's payload concentration, and does it have the size I want it to have? Nanoparticles are booming, and they come in a lot of different forms. Liposomes, lipid nanoparticles, solid lipid nanoparticles, lipid nanoemulsions, polymeric nanocarriers, and many, many more. Particles with their own unique tweak and proprietary content for many different applications. In gene therapy, for example, cancer treatment, vaccine development, and other biopharma. One of the reasons for this abundance of options is the fact that a variety of payloads can be encapsulated. Of course, making nanoparticles an option in a lot of areas. The payloads can be RNA, DNA, protein, or practically any other active pharmaceutical ingredient. And then there is a range of options for each category. For example, for RNA, it can be different types, like messenger RNA, but also small interfering RNA. Stunner tackles these two questions simultaneously. With our nanoparticle apps, Stunner delivers low-volume, high-throughput DLS without the need for dilutions to get the size and PDI data you need. On the same 2 microliter sample, Stunner quantifies your total payload concentration, whether it's RNA, DNA, protein, or any other API, without the need for any reagents, standards, or fluorescent dyes. All this is done in a 96-well play-based format that powers high-throughput analysis of nanoparticle samples, fresh out of mixing. Stunner contains two technologies to read each sample, UV-Vis for concentration and DLS for sizing. Simply add in 2 microliter of nanoparticle sample into the input well, and it's pulled into the microfluidic reservoir. At this step, the sample can sit up for up to 2 hours before reading, with no evaporation. After the plate is loaded into the instrument, the circuit is read first when it's empty, and that will remove any absorbance contribution from the plastic. And then a pump applies a small vacuum, which moves the sample into the microcuvette to be read. Because the circuit has fixed pad lengths, it can make very precise and accurate reads. Stunner's nanoparticle applications combine both technologies on a sample to deliver total payload quantification and low volume, size, and PDI results. Here we can see exactly what sample loading looks like with the help of some fluorescein and a blacklight. In 2 wells, we've already added 2 microliter of fluorescein. As you can see, to load another sample, you simply add in 2 microliters into that input well, and the sample wicks into the plate. On the left, you can see loaded samples, and on the right, the samples have already been measured, and you can see both microcuvettes in the Stunner plate now contain the fluorescein. Nanoparticle size is critical to the performance of a successful drug. Throw a stick in the literature and you'll hit a paper with nanoparticle size data, often showing the link between the size and the effective dose needed. So when you've got lots of buffers, formulations, and RNA constructs to test, you want to be gathering size data of everything. Here we're looking at intensity distribution data for a whole plate of lipid nanoparticles, with z-average diameter noted as the value below each distribution. These messenger RNA lipid nanoparticles had a hydrodynamic diameter of 79 nanometers plus or minus 1%, and a polydispersity index of 0.14 plus or minus 0.02. Stunner will provide DLS results just how you like it, with hydrodynamic diameter and PDI. But now you no longer have to be limited by DLS data that has to be manually gathered for about a dozen pieces of data in a day. Now, DLS can keep up with LNP samples as fast as you can make them, allowing you to run as many replicates as you want. Stenner's dynamic light scattering gives you the high throughput power to gather the size and size distribution data on 96 samples in less than an hour, with just 10 minutes hands-on time to load your samples, where DLS on other systems can take more than 3 hours hands-on time to get through 96 samples. Now we've just discussed the sizing of particles. Now let's talk about Stenner's UV-Vis quantification to get the payload concentration of your nanoparticles. The most famous product with nanoparticles are for sure the latest messenger RNA vaccines. An important factor is of course the dose. Dye-based quantification is multi-step, requires dilutions, uses costly standards and dyes, requires hours of analysis and hands-on lab work, and includes breaking down the precious particle you just made. There needs to be a better way. And you could try to quant with UV-Vis. But nanoparticle solutions have tons of turbidity, so traditional UV-Vis approaches fail. Until Stenner. Load up an LNP sample into a Stenner sample well and you'll quickly see it being wicked into the serpentine reservoir and held there. To read the plate, Stenner will pump the sample into the 0.1 and 0.7 mm pad length cuvettes for UV-Vis absorbance measurements. When reading LNPs, the combination of Stenner's two fixed pad-length microcuvettes provides precision and broad dynamic range. Since LNPs are typically very turbid, cloudy samples, the short pad lengths are needed so that light can pass through and enable absorbance measurements. Now let's take a look at some RNA LNP samples. The empty LNPs create a whole lot of signal that look like absorbance, but it's actually turbidity, and usually isn't helpful and just gets in the way. Because all that turbidity makes quantifying with traditional UV-Vis almost impossible, and total RNA quant by UV-Vis is normally a big challenge. For example, if we squint at the full curve, we can see the RNA bump at about 260 nanometer, but the difference is pretty small. To analyze this, we have to separate out the signal from the turbidity from the signal from the LNP absorbance due to RNA and other LNP components. On the left, we have the raw data again, and on the right, Stenner has used our Unmix algorithms to isolate the impact of turbidity and remove it. This is shown by the black line indicating total signal, and the gray line indicates the contribution from turbidity. The remainder is in green and in blue. Green here is the isolated signal from RNA, and that will be our total RNA concentration. Blue is the UV-Vis absorbance signal from other components in our sample, so UV absorbing lipids, excipients, and buffer components. Stenner separates the contribution of those three groups, turbidity, RNA, and other components, to quantify total RNA concentration in less than a minute per sample from just 2 microliters, and this all without any dyes, reagents, or complicated workflows. Stenner's RNA concentrations agree closely with the total messenger RNA concentration determined by RiboGreen. A twofold dilution series of Firefly luciferase mRNA LNPs showed highly linear results down to 1.2 microgram per ml. Error bars are plus or 1 standard deviation. And as mentioned, Stenner lets you run 96 samples in an hour. Here you can see 96 replicates of RNA LNP, where the green is the RNA concentration, and that's also mentioned below the graphs, and gray is the turbidity signal. The coefficient of variation is a spectacular 1.54% over these 96 complicated samples. Quantification with RiboGreen required standard curves, costly dyes and standards, and a lot of hands-on work, and still just provides limited throughput. While measuring concentration on Stenner will be fast, simple, and doesn't require any dyes or standards. Now, RNA LNPs are of course not the only nanoparticles out there. As mentioned in the very start of this presentation, nanoparticles have a broad area of applications. So let's take a look at some other potential payloads. Here we can see nanoparticles with DNA and protein as payload, and they were measured and provided the expected results. Whether or not you're measuring a pure analyte or an active ingredient inside a nanoparticle, Stunner will deliver accurate and precise data that is linear across its complete range, whatever your nanoparticle payload is. Now we're looking at a special particle that contains RNA and protein. Getting quantification on these is difficult when looking at the total spectrum, since this is a combination of turbidity, protein, and RNA absorbance. But Stunner will analyze the spectrum, take away the turbidity contribution, which is the gray curve, and lets you quantify both the RNA, so the blue curve, and protein, the green curve, component in this custom nanoparticle. So see and measure exactly what you need, and get payload concentration and particle size from just 2 microliter sample. And as mentioned a couple of times, nanomedicine is hot, and new, unique, and proprietary particles with their custom payload are developed rapidly. Teach Stunner all about the UV vis absorbance of your nanoparticles. Shown here is a setup in the software and its results, where Stunner allows you to create your own reference spectra, providing the possibility to set up your custom application and quantify exactly what you're interested in. And this is how it works for your unique particle. You've shown Stunner what your pure API is, and it will deconvolute it from the raw spectrum to get you the result you need. Skip the disruption step and quantify any payload, RNA, DNA, a protein, or whatever small molecule. Stunner makes quantification crazy simple to free you from complicated workflows, costly dyes, and wasteful standard curves. We also have IQOQ procedures available, and Stunner software is 21 CFR Part 11 compliant with full audit trail and electronic signature capabilities. And for labs doing manufacturing, quality assurance, and quality control, Stunner has a performance verification. These tests meets the United States Pharmacopoeia and the European Pharmacopoeia guidelines for UV-vis spectrometers. The tests and all necessary calculations are handled automatically by the software. So analyze it all, concentration and sizing simultaneously from UV-vis and DLS on just 2 microliter of sample in less than a minute for nanoparticles with RNA, DNA, protein, or small molecules as payload. That is how Stunner delivers label-free, standard-free, and hassle-free nanoparticle characterization to the whole nanoparticle world. So with Stunner, you can cut through the fog to see all the spectacular details of your LNPs.